right. Any questions so far? So, any problems with doing the linked list on the worksheet? Yeah.
No, sorry about that. I was going to say something about the ODP.
Okay, go ahead and pass those sheets in just so I can eyeball them. And go ahead with an ODP question.
So I got 10 out of 10, but I got buffer overflow when I assessed it.
You got a buffer overflow.
I went back and I fixed it, but it gave me 10 out of 10 anyway.
That's possible. Yeah, so especially the earlier ODPs, they're kind of simplified. So it's possible your code may not be perfect and you'll still get 10 out of 10. But that will be less and less likely. But that's cool to know. Okay. All right, so I took a look and only 6 people have pushed anything over to GitLab for linked list 1 and added me as a reporter. And I'm not sure why, because it takes, if you know how to do it, it takes about 20 seconds to do, well, okay, about a minute to do. If you don't know how to do it, you really want to figure out how to do it. Thanks. And only 2 people have asked me to check to see if it's available, and I told you that if you do this week, you can send me an email and say, hey, can you read my repository, and I'll check it and I'll let you know, right? Tomorrow's the last day you can do that. If you don't do that, you run the risk of losing at least 25 points on the due date, because 8 o'clock in the morning next Friday, I'm going to download everything, and if I can't get to your repository, can't grade it, you're down 25 points. And assuming you respond to my email after that and you get it fixed, you're okay. But if not, you're going to end up with a 0 after doing, a week plus worth of work on PA1. And there's no reason for it, right? Make a README, just say hello, push it over to GitLab, log on to the website, set me up as a reporter. Okay? Do it as soon as possible. And if you want to know if it works, shoot me an email today or tomorrow and say, hey, I did this, can you read my repository? And I'll double check it for you. And then you don't have to worry about it, okay? So it's a really good thing to get taken care of up front. All right, let's talk about abstract data types. This is a term that gets thrown around a lot. And you'll just see it called ADT. What is an abstract data type? Okay, let's think about the scanf function that we use in C when we want to parse input. And we don't write this function ourselves, we use this. We assume that when we say GCC and we got an scanf, somehow this function is going to come from somewhere and it's going to be made available to us. And we know what it's going to do, right? We're going to pass a string, we're going to pass a format, and we're going to pass a variable, and it's going to parse that string as an integer and store the value in that variable, and if it succeeds, it'll return a 1, otherwise it'll return something different from a 1. Do we know how this function works? I don't know how it works. I could make some guesses, but I've never looked at the source code for fscanf. But it's a safe bet that it's probably got some kind of loop inside that starts from 0 and increments through str, looking character by character, and looks at the ASCII code, and if it's between a 0 and a 9, it records that value somewhere and it multiplies by 10 and adds, and somehow comes up with this version of this string as an integer and then copies it into here and returns a 1. But suppose Intel makes a new processor and it has built into the processor an assembly language instruction which lets you convert a sequence of characters into an integer. And suppose that on the new version of Unix that we get with our laptop, scanf is simply a wrapper around that assembly language instruction. There's no for loop, there's no C code, it just calls this assembly language code, with this string in this format, and it gets back an integer. Do we care about that change? Do we have to modify our main programs? Do we have to go back and rewrite all our 224 code? Absolutely not, right? As long as the interface to scanf is exactly the same. Here's a string of characters, here's a format string, this is what %d means, and so on. Here's the address of the variable we want to write into. Suppose we wake up in a slightly different universe and scanf actually takes this string, changes it into a sequence of musical notes, transmits it to a magic unicorn on Candy Mountain, who stamps out with its foot the number of the integer corresponding to this string, which is sent back to our PC and loaded into the variable. Does that affect our main program? Absolutely not. Okay? So we can think of scanf as an abstract function. What it does is it takes a string, it takes a sequence of parameters, and it takes an address of variables, and it does a conversion according to this protocol, and it writes the results into the variables, and it returns some magic value. And we don't care how it's implemented. Okay, this is how we want to think about linked lists. So let's think about a linked list as an abstract data type. So we're not a 222 student. We're not a computer scientist. We're just a user who wants to store a bunch of data in a computer. We've never heard of a linked list. Right? We just want to store data and be able to pull it out in sorted order. And so what kinds of things do we want to do? We want to do some kind of initialization. We want to be able to do some sort of insertion of data into this collection of numbers. We probably want to be able to search for a number in our collection. We probably want to be able to delete something from our collection. And we may also want to be able to look at everything that's in our collection of numbers. And so this is a process we'll generally call traversing. Traverse is just another word for saying I want to be able to look at all the stuff that's in my linked list. So for example, print out everything in my list with commas in between them. And that may be all we want to ever do with this thing that's called a linked list, right? We want to initialize it. We want to take numbers and insert them. We want to take numbers and delete them. We want to search for numbers. And maybe we want to look at the whole collection of numbers. And in Java, for example, there are a lot of different classes, right? Data types, data structures, that will let us do this with different types of information. There's collections, there's lists, there's arrays, there's all sorts of stuff, right? But from a user perspective, this is all we care about, being able to do, say, these 5 operations. And so our main program might say something like, you know, initialize this list, get a number from the user and insert it. Get another from the user and insert it. Now get a number from the user and search for that. Now get a number from the user and delete that from our collection. Now print out everything that's in our collection. And so as 222 students who are creating a linked list package, a collection of routines, we want to create a series of functions that a main user could call to interact with our underlying data structure. But here's what we don't want to do. Okay, we absolutely, positively, never, ever, ever want to tell the user, the person writing the main program, hey, make a for loop from 0 to 11 and check list bracket index dot valid to see if it's equal to 0 or 1. Okay, that'll work great if this is how we're implementing our linked list. But if our linked list is being implemented by sending musical notes to a magic unicorn, their code's not going to work anymore. Okay, so what we want to do is we want to sort of create this firewall. And on one side is the implementation detail, the stuff that we're writing, the low-level C code, that in this case might say, you know, make a for loop and check the valid flags, and when you find a 0, let's use that for where we store the next number. Okay, that's the implementation side. On the other side of the firewall is the user interface. That's this stuff. This is what the user sees. So all of this is connecting to the lower level code, which is the implementation. But there's this big firewall here. And the user code talks to these routines. These routines deal with the lower level details. But if we decide to change the implementation, we simply change how these routines talk to the lower level details. The user code never has to change. It wants to insert something, it calls insert. It wants to delete something, it calls delete. So as we start talking about PA1, which we're going to do today, right, I want you to try to keep in mind this distinction. We're going to be writing routines to do initialization, insertion, searching, and so on and so forth, and they're going to have to deal with, you know, how do we insert? Well, we'll start with element 1 and we'll check the valid flag. And we'll move through our array till we find something where valid is 0. That's where we're going to do our insert. And we'll set the data field of that to our number we're inserting. Those are the implementation details. But you're also going to be writing a main program which uses a linked list. And the main program is going to let the user say I space 5, and that'll insert the number 5. Or D space 10, and it'll delete the number 10. And that main program should only be doing these things. It should never be looking at an array. It should never be looking at valid flags or data fields or next fields or anything looping through here and so on and so forth. Does that make some sense? So we'll repeat that with more specifics as we go through PA1. All right, so let me talk about the ODP first, which is another piece of PA1, and then we'll look at PA1 full on. So let's look at the next ODP, which is 203. Any issues with ODP 202? Okay, let me spin up some code for 202 just to keep everybody on the same page. So there's my initialization function for ODP 202. So you have to declare what a struct node is. Okay, the main program knows what a struct node is, but when you're compiling this, it doesn't have access to the structure definition from main.o, right? So you have to define what a struct node is in every file that you're going to use it. I used a type def. You don't need a type def. Down here, instead of saying uppercase node, I could have said lowercase struct space node. A type def lets you say, hey, when I say uppercase node, what I mean is struct node. So it saves you from having to say struct every time. But this could just be struct node. Okay, so there's the init function. It's called init. It doesn't return anything. It takes one argument, which I chose to call LL. And that is a pointer to a struct node, or an uppercase node that's an array. And you got to give this thing a name because it's an argument to a function. Okay, if it was an integer, you'd say integer x. And then there's the code we wrote yesterday on the board to set up the sentinel nodes values for data next invalid. And then a loop from 1 to 99 that sets data next invalid to those particular values. And that's all you need. Yeah?
So for structures, I remembered in 121 they did like a list equals and then curly bracket, and then you could just define all your values.
Ah, yeah, yeah.
I kind of forgot the format for that because I was trying to do that last night, but it didn't.
So if you have an array, you can say, declaration array equals curly bracket, and you can do a few things. If you just say 0, I believe it initializes everything to 0. If you list n values with commas in between, it'll set the n values of the array to those n values. I don't think I've ever done it with a structure, though. But I would guess you would simply name the data next invalid in that order, separated by commas. But it would be easy to try. So yeah, that would be good exercise. All right, any other questions on ODP? All right, so let's look at 203. So 203 is going to do this business of let's figure out where we can store a new piece of data in our array. So this is something that we're going to call GetNode. All right, so GetNode is a function that takes an array of struct nodes and returns an integer. And what it does is it starts at the beginning, okay, index 1, and it searches for a node where the valid field is equal to 0. So assuming that this was what our struct node array looked like, and I said get node and I passed this array, get node should return a 4. Okay, it returns the index of the first entry where valid's equal to 0. And if this entry up here happens to be a 0, then it should return a 2. Okay, so this is the business of here's what my structure looks like as an array. I want to find the first node where valid's 0. GetNode is just a function that does exactly that. And I would start searching from index 0. Don't treat the sentinel node as special. So if you're implementing your list and you have a sentinel node, set the valid flag to 1. Okay, just to keep it clean. And so you get node functions that start from the first element in your array, index 0, check to see if valid is 0. So it's a loop, right? If you pass it a struct node pointer called list, just make a loop for I equals 0 to 99, and if list bracket I dot valid equals 0, return I. If you get to the end of your array and none of the valid flags have been 0, they've all been 1, that means there is no space left in your structure. And so you return -1 as an error code. Yeah?
So how do you determine when you hit the end of the array?
So I should say in here, and maybe I don't, that your array has 100 elements.
Oh, okay.
But I don't think I say that in here. So let me be really sure. Talked about PA1 already, so we'll do that right after this. All right, so this makes sense? So it's a for loop. Inside the loop, check to see a valid 0. If it is, return the index you're at. If you get to the end of the for loop after checking 100 entries, just return a -1. It means you're out of space. All right, write some test code, set up different values in your array and make sure that GetNode does the right thing, and then link it into your test bed with this and assess it like that. All right, so let's look at programming assignment 1. So PA1 is implementing a linked list using this array-based approach. So your list is an array of struct nodes. Your struct node is, you know, what we've been playing with. Integer data, integer next, integer valid, in that order. Data, so this is a linked list of integers. Data is the actual integer that's stored in the list. Next is the index of the next element in the array, or -1 at the end of a list. And valid is just a flag. 1 means the node's valid, 0 means it's not valid. Meaning either you've never used it or you've deleted it. Okay, very, very important. I do not want you to write the number -1 in your code. I want you to make a symbol called myNull and define myNull to be a symbol that's equal to -1. And if you want to check to see if a valid flag is equal to, or if a next flag is equal to -1, don't say if field.next equals -1. Say if field.next equals myNull. Okay. It's a silly sounding point, but it's very, very important. It's going to make a big difference on PA2. So myNull, right, just do that define. And now anytime you say myNull uppercase, the compiler will basically replace that with -1. So you could say, you know, ll bracket I dot next equals myNull. Okay, in your main program, you're going to declare a struct node called list containing 100 struct nodes. Okay, that's the actual linked list. And that's the one thing that your main program does that is not totally independent of the implementation. That's just because it's C, and C doesn't quite support this as cleanly as we'd liked. Okay, so your main program, set up a struct node list bracket 100. And it's got to be done like that. It can't be struct node asterisk list. You'll segfault. Okay, you got to say I want 100 struct nodes. Okay, you're required to implement the following functions. The first one is called init. This should not be difficult because you've already done this. Okay, init should initialize LL to be an empty linked list, meaning that the element at index entry 0 should have a next value of myNull, valid flag of 1, and a data value of whatever you feel like putting in the data value. All right, there's an add function. Add takes 2 arguments. It takes the linked list array, okay, so the pointer to a struct node, and it takes an integer. And it should insert that integer into the linked list in such a way that the list is still sorted, smallest to largest. So this was some of the pseudocode we spec'd out yesterday, right? First you have to figure out where you want to insert in the list, and then you take the node right before and you have it point to your new node, and you have your new node point where the prior node used to point. And we're going to go through this on paper in some examples. But that's inserting into your list. Okay, so that's got to be a function called add. Takes a pointer to the struct node array, takes an integer, and it returns a flag saying success or not success. Okay, normally you try to insert something into a list, it's going to succeed. The one possibility is you're out of space. So your add function is going to have to look at your array and say, well, let's find an entry where valid is equal to 0. If it checks all 100 entries and valid is set to 1 on all of them, there's no space left in the linked list. You cannot add something, so the add function returns 0, saying I did not succeed. Okay, print is our traverse function. It takes 1 argument, which is the linked list array, does not return anything. And all it does is it follows the linked list from the sentinel node to the end and prints out each data value. And this is not the same as just going through your array from 1 to 100 and printing out the contents of the data field. That's not traversing your list. That's looking at your underlying data structure. Traversing means start with the sentinel node, see where it points to, go to that element, print out the data field. See where that points to, go to that element, print out the data field. Keep doing that until it points to my null, and then you're done. Just return. So when you call traverse, the list of numbers printed out should always be in sorted order, smallest to largest. All right, delete takes linked list and a node, linked list and an integer, finds that integer in the list and deletes it. And it returns a code saying it did succeed in deleting or it did not. If you try to delete something that's not in the list, it should return a 0 saying I didn't find that, I couldn't delete it. Okay. Otherwise, take the prior node, point to the thing that the deleted node used to point to, and set the valid flag on the deleted node back to 0. Okay, search simply goes through your list and looks for a node. So give it the linked list array, give it an integer, start from the sentinel node, see what it points to, keep following through as if you were traversing, but instead of printing, just compare each node's data field to the thing you're searching for. As soon as you find that number, you can just return a 1 right there. If you get to the end of the list and you haven't found the number, return a 0. Say this number is not in the list. Okay, and these are the only functions that your main program should have to use from the linked list code that you're writing. Okay, so you're going to write a main program, it's going to initialize, it's going to do some adds, deletes, searches, and prints. All right, you also want to write the following routines, and these are going to be used internally by your linked list code. These won't be used by the main program. The first one is called GetNode. Hey, that's ODP 203. Okay, what does GetNode do? It starts at the beginning of your array, moves through, and looks for a spot where valid is equal to 0. As soon as it finds one, it sets the valid flag to 1, and it returns the index of that node. If it gets all the way to the end of the list, and all the valid flags are already set, it returns my null. Okay, not -1, but my null. And whenever you're looking for a node to insert something into, I want you to do it by calling GetNode. Your add function, I don't want you to put a for loop in there that checks valid flags. I want you to call GetNode. Okay, going to be really picky about this segmentation into who's doing what in your code, and you'll thank me for it on PA2. Okay, release node does kind of the opposite of GetNode. Once you've decided you're deleting a node, you searched your array and you decided, okay, I'm trying to delete a 12, that's element 3. We need to adjust the pointer so the previous node skips over element 3, right? And then what we were doing is we were setting this bit back to a 0, right, the valid flag. Instead of setting element 3's valid flag back to 0, I want you to call a function named release node. Release node takes the array and it takes the index of the number you're trying to delete, and it sets its valid flag back to 0. Okay, what's your main program do? Your main program is going to let you test your linked list code. Let you test being able to insert things, search for things, print for things, and so on and so forth. Okay, but again, the main program should never manipulate the data structure directly. It should never directly interact with the array. It should do it through these routines we described in the beginning. Okay, so the first thing your main program does is initialize an empty linked list. So that's the init function. And then it prints out a prompt. That's just a greater than sign. And it sits there and it waits for the user to type something in and hit enter. And the user is going to type in a command, hit enter, and then your program is going to execute that command. And it's a very, very limited set of commands that you can do. You can say I space followed by an integer. And that's the user asking you to insert that number into your list. And you should print out one of 3 messages afterwards. Success, meaning you inserted it. Node already in list, meaning you searched and you found that integer was already in the list and you're not going to insert it twice. Or out of space, meaning that you've used all 100 elements in your array. Okay, and that should be it. I say I space 5, enter, I get exactly one of those 3 messages back. Success, node already in list, or out of space. Okay, if I type P followed by enter, that will print out the contents of the list on one line with the numbers separated by spaces. 2 space 5 space 12. If I say S space number, I get back one line that either says found or not found. If I say D space number, that deletes the number from the list if possible. And it prints out either success or node not found. If I say X, exit the program. If I say anything else, print out some kind of short help message, which says, hey, here's the legal commands, right? I space number, P, S number, D number, or X. And after you've executed a command, print out another prompt greater than sign, wait for more input. Okay, so it's a very kind of rarefied user interface. I'm kind of curious if I've actually got a sample of this written. That would have been a good thing to do. I'm a little embarrassed to try this because it probably doesn't do what I just said. Let's see, there's my prompt. So I can say insert 5, insert 10, insert 2, print. There's my list, 2, 5, 10. I can say insert 5, it says node already in list. I can say delete 5, it says success. I can say print, there's my new list. I can say delete 5, it says node not found. And that's pretty much it. That's your whole program. And if I type something else, it gives me a usage message which says, hey, here's the legal commands. And I can search and I can exit. So when you're done, right, there's a lot of code under here. When you're done, it's a very nice and clean user experience. Alright, so deliverables, all the above routines implemented as described. Main program which tests these routines and operates as described. Lots of comments, okay? Every function should be commented. In the beginning of each function's code, put down the name of the function, what it does, right, in your own words, what the inputs are, what the outputs are, any weird side effects, anything the user should know about this, right? So document each function. Put a comment block in the beginning of each file with your name, class number, assignment number, etc., etc. And the make file. Okay, so I recommend doing this in different files. Have a file for your main program, have a file for your linked list functions, maybe have other files too, but at least have those two. Have a .h file that defines your structure and defines the value of my null, right? And then include that .h and whatever .c files you have. Make a make file to put all those together. And then push it over to GitLab in a repo called linked list 1. Make sure I have reporter access. And you're good to go. That's all of PA1. So the main part of, there's two parts to this. Probably the main part of this to worry about is writing these functions. Right, because this is the linked list part, this is the new part, this is the kind of weird part. The main program is very similar to stuff you've been doing in 224. Right, you do fgets to read the input, you do scanf, 20 different ways to figure out what the person typed in. Look for an I space %d, look for an S space %d, check the return value, all that stuff. Okay, so that takes some work, but it's not new. The way that this stuff is potentially new. But you can develop this in pieces, right? You've already written the main program where you set up an array of struct nodes. You've already written an initialize function. You'll be writing a get node function today, right? So you've got some of these pieces set up already. So I would write an add function next. Function that takes this array of struct nodes and a number and adds it to the linked list. And you can always change the assignment, right? You don't have to do things that are written there until you're ready to actually turn it in. So here's something you can do. You can make a different version of the add function, which says, here's my initial linked list. I've got a sentinel node. I've got, 42 or whatever in there, and I've got my null here. So it's not pointing anywhere. Okay, if I say add, so let's call this LL. If I say add LL, comma 10, I should make a new node, give it a value of 10, have the sentinel point to that, set this equal to my null. If you like, you can start off by not worrying about keeping things in sorted order. You could say add is always going to add to the start of the list. That's a fair bit easier than keeping things in sorted order, but it still requires you to work with this structure and to think about pictures and to think about your sentinel node and to do probably 80% of all the kind of weird gushy stuff involved in doing a full insert, right? But this is easier to debug, it's easier to write the code, it's probably easier to think about. So if I say add a 20, and I'm going to add that to the beginning of my list. I'm not going to worry about sorted order for version 1, right? How do I add a new node to this? Well, make a new node that's calling your GetNode function and saying, hey, index element 2 is available. Okay. Set the data field equal to what we're trying to insert. And then set the next field equal to whatever the sentinel's next field is. Sentinel next is pointing down here. Have your new node next point there. And then set sentinel next to point to this new node that you just created. Now we've put a 20 in the beginning of the list. So you don't have to search, and you don't have to worry about where the previous node is and all this kind of stuff. You're always going to change the next field on your new node to be wherever the sentinel's pointing, and then change the sentinel to point to your new node. That's a really, really good exercise to scratch your head over, right? In terms of, here's my structure, I'll set up my original sentinel node. And when I want to insert, how do I figure out where to put it in? Well, that's the GetNode function. And then write the 2 or 3 statements to say, set this new node's next equal to sentinel's next, set sentinel's next equal to the index. But once you get that working, you are off and running. Okay, once you get this working, you can call add 5 times, right? And just make a program, forget about inputs and scanf and all that kind of stuff. Just call add a bunch of times. Alright, so we're going to add 10, 20, 15, 11, and negative 100. And I should end up with a list that looks like this. Right, has 5 numbers in that order. So now write your print function. And print is pretty straightforward if you get it right. But you gotta get it right. So how do we print? Start from the sentinel node. Right, I mean, we did this yesterday. Start from the sentinel, see what next is. If it's not my null, go to that entry and print out the data field. Now look at the corresponding next value. If it's not my null, go to that entry, print out the data field. look at the next. If it's not my null, go to that index, print out the data, look at the next. If it's equal to my null, just return, you're done. And when you do that, right, print should print out the numbers that you inserted in the opposite order that you inserted them. Okay, once you do that, you've got your init working, you've got your add working, you've got your print working, now you can work on delete. And delete will require you to look through your list and figure out what you want to delete and what came right before it. So we'll play with some pseudocode for that in a minute. Or you could write search next. Right? Search is just doing the same thing as print, but instead of printing, just check each data value, see if it matches the thing you're searching for. If you get to the end, return 0, otherwise return 1. So then write delete, and once you've written delete, then you can go back and you can modify add to put things in sorted order. And we can do this without any fancy main program, right? We can just keep saying add, and then we can say delete. LL, comma 20, and then print. And we should see our list with the 20 missing. And then I would say after you've got this linked list code working, then go start working on your main program. And that's the fgets and the scanf and the if statements and the while loop on the outside and all of that stuff. Okay, questions so far? Yeah.
Can your print and search function be the same function, or do you want us to separate them?
What do you mean in the same function?
Because we do very similar stuff. We could just put them into one function that have an if statement saying it, print, then fix it all.
Oh, so I want the interface to be rigorously defined. So I want search to take a linked list array and an integer, right? And I want print to just take a linked list array. But if you want to write an internal function called print or search that takes a flag that says should I print or should I search, and then call that from these two, that's great. Definitely be a good way to do code reuse. But make sure the user has those two functions. So when I talk about the user, that's really you also, right? But it's whoever might be writing the main program. So imagine you're implementing these functions and then you hand it to your evil twin who's going to write the main program. Okay? And they are just going to use these functions. So, but we're the user and we're the implementer of the linked list. But try to think of them as separate tasks. Okay, so let's think about deletion. So let's have a list with a 10 and a 20 and a 30 and a 40. And that's the end of it. This is my null. And so the sentinel node might point to index 3, which has a 10, and that might point to index 5, which has a 20, and that might point to index 1, which has a 30, and that might point to index 2, which has a 40, and that might be my null. So there's a possible picture of what our array might look like for this linked list. And you know, when you're first building your list, if you put your nodes in order, they're going to be successive in the array, but after you do some insertions and deletions and more insertions, this will get all jumbled up. So our first node is actually down here at index 3, our next node is way down here at index 5, and then we jump up to index 1 and 2. Okay, so they might be jumbled up. Okay, let's say we want to delete the 30. The first thing you have to do is find the 30 in your list. Okay, Okay? I recommend calling your search function before you do anything else and make sure the 30 is in there. Because it'll save you from having to deal with a special case in your delete function, which is I got through my whole list and I didn't find it. Right? Call your search function. You've already got a search function. Just call search, and if it returns 0, you can just say, yep, didn't find a node. Just return a 0 from delete. So if you do that, you know that when you're in your delete function, whatever you're trying to delete does appear somewhere in here. Okay, so I don't have to worry about running out of nodes. So how can we do this? Well, previous equals 0. That's the prior node's index, starting off with the sentinel node. If I do LL bracket previous dot next, that's the next node's index. So initially, previous would be 0, current would be LL bracket 0, that's this entry, dot next, that's a 3. So current will be element 3, previous will be element 0. And I'm going to draw this on my picture as follows. This is previous, this is current. And I want to know, is the current node the one I'm trying to delete? So this is delete n. So if LL current.data is equal to n, then I want to delete my current node. All right, how do I do that? Basically, I would take the previous node and I would change it to point where my current node is pointing. So first time through, right, LL current data is 10. That's not the number I'm trying to delete, so I'm not going to do my if statement. Okay, what I want to do before I go back up to the top of my loop is I want to move these pointers down one spot in my list. I want this to become previous and this next node to become current. And that's a pair of statements. So I can say current equals LL bracket current dot next, and previous equals LL bracket previous dot next. So current is being redefined to be whatever current is pointing to. LL bracket current dot next is 5. This is going to become current. And LL previous dot next is 3. This is going to become previous. And in terms of pictures, I've changed this to previous. I've changed this to current. And then I'm just going to go back up here. And I'm going to say if the current node's data is equal to n, let's delete it. And it's not, so I'm going to do this again, and this is going to become previous and current. And now when I check current node's data is equal to n, current is 30, that data does match n, I want to delete current. Okay, how do I delete current? Change the previous node to point where current is pointing. So we did this yesterday. LL bracket previous dot next equals LL bracket current dot next, and then release the current node, which will set its valid flag equal to 0 and return. So there's pseudocodes, mostly C code, for a delete function. Exactly the same thing for insert, right? This idea of having a previous and a current and marching through so that when you get to the spot where you want to insert, you have something telling you what the previous node was, and you can set its next field accordingly. All right, so we'll pseudocode insert tomorrow, and that should be enough for you to make good progress on this. Yeah.
For PA1, the GetNode and the release node functions, do those need to be specifically named GetNode and release node?
Yeah.
Okay. All right, thanks.
Yep.